Hello everyone, this is a video on process synchronization. I just introduce why process synchronization is required in this session. Let us consider multi-programmed environment where we are running multiple processes concurrently. And when we have multiple processes, these processes can be classified as cooperative process or independent process. Cooperative or independent. What do you mean by cooperative process? A cooperative process is one that can affect the other process, or it can be affected by other processes running in the system. Normally, cooperating process will have something common that can be shared between them. They can either share the logical address space which contains code and data, or they can share data only through files or messages. If they are sharing code and data, that can be achieved using threads, which we have already learnt in our earlier sessions. Concurrent access to shared data may may result in data inconsistency. To understand the concept of cooperating process, let's consider the producer-consumer problem. Let me forward the slide. Okay. This producer-consumer problem is a representation of the operating system. What is a producer process? It is a process that produces information that will be consumed by the consumer process. For example, if you are considering assembler as a producer, it will produce the object code which is consumed by the loader. Similarly, the web server and web browser also have this producer-consumer relationship. To allow producer and consumer process to run concurrently, we must have a common area of memory where they can share the information. That area, normally we call it as buffer. To allow both producer and consumer process to run concurrently, we must have a buffer which is shared between them. Normally, producer will use this buffer. Producer uses this buffer to fill the data in, and consumer will use this buffer to consume. Okay. A producer will fill this buffer, consumer will empty this buffer. Please note, buffer means it is a region of memory which is shared by both processes. The producer and consumer must be synchronized, means consumer must not ever try to consume an item that has not yet been produced by the producer. Such form of synchronization needs to be achieved. Also, we need to learn about different types of buffers available. There are two types of buffers that exist. One is bounded buffer and another one is unbounded buffer. As the name only suggests, in case of unbounded buffer, it does not place any limit on the size of the buffer. You can have infinite sized buffer, while the bounded buffer assumes a fixed size for the buffer. And in case of bounded buffer, we have an additional constraint that needs to be considered. The consumer have to wait if the buffer is empty. Likewise, producer have to wait if buffer is full. If buffer is empty, there is no item to consume for the consumer. That means consumer has to wait. Similarly, if buffer is already full, there is no more space to hold the newly produced item by the producer, in which case producer has to wait. And normally this buffer is implemented as a circular array which will have two pointers like in and out. Normally in points the next free space where the next produced item should be placed, and out generally points to the item that should be consumed next, which is also the first full position in the buffer. I repeat, in points to the next free space where the newly produced item has to be dumped, and out points to the item that should be consumed next by the consumer. Okay. The producer process has a local variable called as next produced. If we see the code, we will understand. There is a local variable used here called as item. Both producer and consumer process has a local variable called as item. To hold a newly produced item or to hold an item that has to be consumed. If we are looking at the consumer process, this item is used to hold the item that has to be consumed. Similarly, in the producer process, this item is used to hold the newly produced item that has to be put into the buffer. And we also maintain an integer variable called as count, which is at the beginning will be initialized to 0. We can say that buffer is empty when we'll make note of this. We can say that buffer is empty when count is equal to 0. And we can say that buffer is full when count is equal to the maximum buffer size. Okay. So now with this basic concepts, we can understand the code of the producer and consumer process. Please have a look here. When count value is equal to buffer size, it indicates that buffer is full. And when buffer is full, we already know that producer cannot produce a new item because there is no space to hold it in the buffer. So while count is equal to buffer size, we are doing nothing. Otherwise, if count is not equal to buffer size, means count if it is less than the buffer size, then you can produce an item which is temporarily held in the local variable called as item, through which it is passed on into the buffer to the position pointed by in, and afterwards we are incrementing the in pointer by 1, and we are having a wrap around queue here, circular queue we are having, because our size of the queue or the buffer, it is limited. When you are reaching the maximum size, you are going back to the first position of the queue. So to achieve this, we are using this modulus operator here, and whenever you are pushing an item into the buffer, you are incrementing the count value by 1. I repeat, when buffer is full, the producer cannot proceed. Otherwise, it will produce an item which will be put into the buffer pointed by in. After dumping in this, we are advancing the pointer to point to the next free space available in the buffer. Also, we are incrementing the count value by 1. Now we will look at the code for consumer process, and we know that in the consumer process, if count value is equal to 0, that means if there are no items that can be consumed, consumer has to wait till the buffer is populated with few items, right? So if count value is equal to 0, consumer is not doing anything, it is simply in the waiting state. Otherwise, it will remove an item from the buffer from the position pointed by out. From the position pointed by out in the buffer, you are picking out an item and you are temporarily holding it in local variable called as item. And after doing this, you are advancing the out pointer by 1 to point to the next valid item in the buffer. and also we are decrementing the value of count by 1. So during the producer process we are incrementing the count value by 1, and during the consumer while running the consumer process we are decrementing the count value by 1. After we have understood the code, let's see what happens when both the process execute concurrently. Please understand that producer process all alone will work fine, and consumer process if run independently will work fine. Now we are considering a scenario where we are trying to run both the process simultaneously. As an example, let us assume that the count value we are initially assuming it to be equal to 5, and we are allowing both producer and consumer process to execute the statement count plus plus and count minus minus. Okay, concurrently. Count plus plus is present in producer process, count minus minus is present in consumer process. We are allowing concurrent execution of these two statements from two processes. Using common sense, we can say that when we are incrementing a value by 1 and we are decrementing a same value by 1, the result will not alter, right? Now what we have assumed is count value we have taken 5, we incremented it, count plus plus we did, which will make the count value as 6. Then we will make the decrement of the same value, which will result in 5 again. So increment and decrement by 1 should yield the earlier result itself. But are we going to get the same thing? Let us see when we do the concurrent execution. Okay. Here we get an interesting result which always depends on order of execution of two processes. The result of count value can be either 4, 5 or 6, depending on in which order the execution of the instructions happened between two processes. To understand how values of count is updated with incorrect result, let us see typical machine language equivalent statements for count plus plus and count minus minus. Here it is. Count plus plus is a high level language statement. If it is converted into machine language statement, it would typically look like this. Will fetch the value of count into a register. After fetching the value into the register, we are incrementing it and we are storing back the content to the memory named as count. Similarly, count minus minus in the machine code will look like this. Count value fetched and updated in register 2, and we are decrementing the value of register 2 by 1. Also we are updating the register 2 contents into the memory location called as count, right? And we now consider the concurrent execution of count plus plus and count minus minus. Doing sequential execution of these 6 statements. Here we are having 6 statements, 3 for count plus plus and 3 for count minus minus. If we are executing these 6 statements, normally they will be interleaved in some arbitrary order. One such interleaving is shown in this slide here. We have obtained incorrect result. You can see that at time 0, producer process is executing the first statement. Count value initially, which is 5, is moved to register 1. And at time t1 also producer process itself is executing the second statement. Register 1 is incremented by 1. Now the register 1 content is 6. Now there is a context switch between producer to consumer process. Consumer process has started its execution and it is running its first instruction. What is the first instruction? Count value fetched and dumped into register 2. What is the count value? See, we have updated the count value. We have incremented it by 1, but that is not reflected in the memory count. We have done updation only in the register, right? So while the consumer process is trying to fetch the value of count, it is still 5, right? And at time t3, again consumer itself gains the CPU access, so it is executing the second instruction, register decrementing. Now the register value is decrementing by 1. We are getting 4 here, and at time t4, producer process has gained access of CPU and it is executing its next instruction. First two instructions are already executed. Third instruction it is going to execute now, where it is writing the register 1 contents into the memory location count. So now you can see that count variable is updated to hold a value of 6. At time t5, consumer process has gained access and it is executing its last instruction, that is count is equal to register 2. Now register 2 value, which is 4, is updated to the count. So what is the last value that has been updated? It is 4. It is 4. By this example, you might have understood how the order of execution of the instruction can change the final outcome. And to get a clear idea, you can just interchange or reverse the order of statements T4 and T5. If you execute consumer first and then the producer, then what happens? You are writing 4 first to the count, and in T5 you are writing it is 6 to the count value, in which case the final outcome will be 0. So we are getting incorrect value because we are allowing two processes to modify same memory simultaneously. Now let me introduce you all a term called race condition. Race condition. This is a situation where multiple processes access and manipulate the same data at the same time, and outcome depends on order in which access takes place. I repeat, race condition is a situation where multiple processes are accessing and manipulating the shared data at the same time, and the outcome or the final result which will be retained in the shared memory, it always depends on the order in which the access has taken place. Okay, this is a problem. To prevent the race condition, we need to ensure that only one process should be able to manipulate the shared memory at any given instant of time. We are allowing two processes in case of producer-consumer problem to manipulate the same data. What was the shared data there? Count we were modifying. Count is modified by producer process as well as consumer process, right? We have given access of the shared variable to both the process, and both were trying to modify the same variable at the same time. That is why we were getting the wrong result. So that condition itself is called as race condition. But to prevent the race condition, we need to ensure that only one process gains the access of the shared resource so that it can manipulate it at any given instant of time. To make such a guarantee, we require that process to be synchronized in some way. Okay, so this is an introductory video on process synchronization. That's all for this session. Let's catch up on a new topic where we are going to learn how process can cooperate using what is called as critical section problem in my next session. Thank you. Hello everyone, this is a video on critical section problem. With the help of producer-consumer problem, we have already understood that concurrent access to shared resource may lead to unexpected outcome. What do you mean by shared resource? The resource which was shared among multiple cooperating processes. So what are typical examples of shared resource? Then it can be a data structure like count, which we have used in our producer consumer problem, or it may be a peripheral device like a printer, or it can be a network connection as well, or it can be number of open files that are shared between processes. So what's the point here is we are not supposed to allow concurrent process to manipulate this shared data simultaneously. If we are allowing it, it will always lead to inconsistent data. That is called as race condition. That is what we have discussed in our earlier video. Simply put, we have portion of the program in memory. We have portion of the program in memory which tries to modify the shared resource, and that portion of the program has to be protected in such a way that only one among the multiple processes are executing that piece of code, while others are not trying to execute that protected area where you are manipulating the shared resource. So let us see a typical structure of a process. Here you can see that each process will have a segment of code called critical section. Here you can see that each piece of code will have a segment of code called critical section, which is responsible for manipulation of the shared resource. This critical section contains code which will manipulate the shared resource. What is example for this? Speaking back to our earlier example, we had statements like count plus plus or count minus minus, which altered a common variable or a shared variable called as count. So whenever you try to execute these statements in your process, that should be kept in a protected section called as critical section. An important feature of the system that supports cooperating process is that when one process is executing in its critical section, then no other process are allowed to execute in their critical section. What do we mean by that is, when producer process is altering the shared resource, then consumer process is not allowed to alter the shared resource. Okay. I repeat, important feature of the system that supports cooperating process is that when one process is executing in its critical section, then no other process are allowed to execute in their critical section. To ensure this, each process must ask permission. Each process must ask permission to enter into its critical section, and this piece of code is called as entry section. What is entry section? It contains code where a process asks permission to enter into the critical section. And the section of code which immediately follows critical section, we call it as exit section, and all remaining code in the program, we call it as remainder section. I hope the concepts are clear here. I repeat this is an important concept that has to be understood clearly. This is a general structure of a typical process. Each cooperating process will have a portion of the code. This is a protected section of our code. This is called as critical section. And normally we will write such a code in critical section which will try to manipulate the shared resource. Okay, and there is another piece of code that is responsible for asking permission to enter into the critical section. That piece of code we call as entry section, and what follows critical section is exit section, and whatever writing apart from these three sections in your program, all that will be called as remainder section. Okay, I'll move forward the slide. So now we are going to learn solution to critical section problem. A critical section problem solution must satisfy three requirements. The three requirements are mutual exclusion, progress, and bounded weighting. The three requirements to solution to critical section problem. What is mutual exclusion? Mutual exclusion means if some process is executing in its critical section, then no other process in the system can be executing in their critical section. I repeat, mutual exclusion means if process PI, for example, is executing in its critical section, then no other process are allowed to execute in their critical sections. Okay. And at any given instant of time, many processes may wish to enter critical section at the same time. So there is a race among multiple processes, but there is a criteria for entering into the race. Who should participate? Only those processes can participate which are not executing their remainder section, and also selection of which process should enter critical section cannot be postponed for indefinite time. This property we call it as progress. I repeat, if no process is executing in its critical section and if there exists some process that wish to enter their critical section, then selection of the process that will enter critical section next cannot be postponed indefinitely, and also in the race only those processes can participate which are not executing the remainder section. Okay, this is the second property or second requirement, and the third requirement is bounded weighting. Let us say there are n number of processes wishing to enter critical section, and one process didn't win the race. Now we need to understand how far OS can let the that process which didn't win the race has to wait. There is a limit defined. There is a limit defined on how many times other processes are allowed to enter their critical section before the requested process request is granted. I repeat, there will be a bound on the number of times that other processes are allowed to enter their critical section after a process has made a request to enter its critical section and before that request is granted. Just to make you understand, let's say if the limit value is 3 and P1 has requested to enter into the critical section, before OS can serve this request, maximum it can allow 3 other processes to enter into their critical section. Once it has granted 3 other processes, not P1, 3 other processes to enter their critical section, P1's request has to be served. This requirement we call as bounded weighting. So what we just learned is requirements. We learned requirements for solving the critical section problem. There are 3 requirements: mutual exclusion, progress, and bounded weighting. Before I proceed to the next topic, I just want to add one more concept here. At any given time, many kernel mode processes may be active in operating system. For example, consider a kernel data structure that maintains list of open files. There can be a data structure like a table which maintains all the files which are currently open in the system, and this data structure here, it is modified as and when a new file is opened, an entry is made into this table. Also, when a file is closed, an entry is deleted from this table. If 2 processes open file simultaneously, this results in race condition. Okay, there are many such data structures used by the kernel where that could lead to race condition. To ensure OS is free from such race conditions, 2 approaches are generally being used. The first approach we call it as preemptive kernel, and the second kind of kernel is non-preemptive kernel. Okay, a preemptive kernel allows process to be preempted while it is running in kernel mode, and a non-preemptive kernel does not allow process running in kernel mode to be preempted until it exits kernel mode or voluntarily gives back control of the CPU. And it's quite obvious that non-preemptive kernels are free from race condition. But why one would opt the preemptive kernel while designing is it is more suitable for real-time programming, because high priority real-time process can always preempt currently running low priority process. And now we try to learn a solution to the critical section problem. We will learn both software based solution as well as hardware based solution. Moving ahead, let us learn a software based solution to critical section problem called as Peterson's solution. Peterson's solution is a classic software based solution to the critical section problem. Solution to critical section problem, as we have already understood, should satisfy three requirements. The three requirements are mutual exclusion, bounded waiting, and progress. First, let us learn the solution. Then we will see how these three requirements are satisfied by Peterson's approach. Also, please note that this solution is restricted to only two processes. Okay, and the two processes share two variables in common. The shared variables in case of Peterson's solution among two processes are turn and flag. What is this turn? It is an integer variable which is used to indicate whose turn it is to enter into the critical section. And if turn value is I, that indicates that process Pi is allowed to enter the critical section. And if turn value is j, for example, that indicates that process Pj, it is process Pj's turn to enter the critical section. Okay. We have also used another shared variable called as flag. This is a Boolean array and it is used to indicate if a process is ready to enter the critical section or not. It is used to reflect the readiness of the process to enter the critical section. If flag of I is true, means Pi is ready. Similarly, if flag j is true, means Pj is ready to enter critical section. Let's say if both process Pi and Pj are ready to enter into critical section, that case Pi and Pj both are ready. In that case, what happens is this flag I will be equal to flag j both set to true. If both processes try to enter critical section at the same time, they will also need to set the turn value. Turn value should be set to either I or j. And if both try to write on turn at roughly the same time, only one of these assignment can be retained, other should be overwritten. So based on the turn value, it can be decided that which process will enter critical section. Next, let us learn the general structure of a process in Peterson's app. Let's forward the slide and let us see the structure of process in Peterson's solution. Observe the code carefully. You can see that when Pi is executing, it will set flag of I to true and it will also set turn is equal to j. turn is equal to j. That means it is offering a chance to process pj, another process. This process pi is offering a chance to another process to enter critical section by setting this turn value to j. And any process can enter to critical section only when other process flag is set to false and its turn should be set. Please observe the code. While flag value is flag of j is true and turn is j, that means that process pj is executing its critical section, in which case this process has to wait. It will loop in this statement itself, checking the condition of flag of j and turn value. Only when one of these two values change, then it can enter into its critical section. And also in the exit section, you can see that it is making the flag of I value to be equal to false, and this code is responsible for satisfying one of the requirement of critical section problem, that is not one of the requirement, two of the requirements, that is progress as well as bounded waiting. And here we have the remainder section. Please note this turn value setting and flag value setting will be the entry section of the code, and the while statement here, this is the entry section and here is our critical section, and setting back the flag value to false will form the exit section of our code. And here you can see to the end of our program we have remainder section. Now let us see how the three properties or three requirements to critical section or being handled by this piece of code here. As I said, any process can enter to critical section only when other process flag is set to false or its turn should be set to true. This means pi can enter into critical section only when either flag of j is false or turn is equal to I. Let me try and clear this area here. Okay, so if flag of 0 equals and flag of 1 is also equal to true, if flag 0 is equal to flag 1 is equal to true, we have taken I and j, flag I and flag j, if it is equal to true, that means both processes are executing in their critical section at the same time. This implies that both pi and pj cannot be executing while statement at the same time, because value of turn can be either I or j but not both, right? Turn cannot have two values. It is single integer variable where you can store any one of the value, either value I or value j. So this ensures that mutual exclusion is preserved. However, flag I and flag j can be true at the same time, and this will prevail as long as one of the process is executing in its critical section. When one process is executing in its critical section, flag I and flag j both value will be true. But on the exit section, on the completion of critical section, whichever process was executing in its critical section will make the flag value to false. When flag value becomes false, then you can proceed with the critical section entry to the other process. To prove second and third properties, please note that pi will be prevented from entering into critical section only if it is stuck in the while loop. Only possibility of not entering into the critical section is ensured by this while loop here. By this while loop, right? So if pj is not ready to enter critical section, then flag of j will be false. So pi can enter. If pj has set flag j to true, Then PJ will enter critical section and on exit it will reset the flag value to false, which allows PI to enter critical section. So this is how Peterson solution solves critical section problem. And that's all for this session. In the next session, let us learn hardware solution for critical section problem. Thank you.